So, before going for this theorem, Heine Borel theorem, Weierstrass theorem, we require one or two lemmas which will be needed in the proof of these results. We have seen already proved the following theorem, that if I n, where the I n is say closed interval a n b n, is a sequence of intervals in R 1, that is real line, interval of the real line, closed interval real lines, such that they are of decreasing nature, such that I n covers I n plus 1 and so on, for n is 1 to 3 and so on. Then the intersection of I n when n is 1 to infinity, countable intersection of I n is non-empty. This result we have seen. Now, extending these results, we can extend this result to R k space. Let k be a positive integer, if I n sequence I n be is a sequence of k cells, such that I n covers I n plus 1 for n is say 1 to 3 and so on. Then the countable intersection of these cells 1 to infinity I n is not empty. So, the proof runs on the similar line as we have done it. What we will do is we will fix up say j, each I n j we can take it for fixed j and apply this one. Okay. This proof we will get the result. So, I am just dropping what we are interested, which is important part here, that each or every k cell is compact. Every k cell is compact. So, one cell means closed interval, two cell is a rectangle, closed rectangle of course, and third cell, fourth cell and like this. So, every k cell is compact. So, let us see the proof of this first. Suppose I be a, let I be a k cell consisting of all points of the type say x 1, x 2, say x 1, x 2, x k, such that the x j lies between the bond a j less than equal to v j, j is 1 to k. Let this be a k cell. So, here this is our set k is 2. So, it is in I 2 and this I in 2 cell means it is in k is equal to 2. So, we are having the cell like this, where the x 1 vary from a 1 to b 1, while the x 2 vary from a 2 to b 2, Say this is our here. So, here this is x 1, this is x 1. Okay. So, this will vary from a 1 to b 1, and here is x 2 which vary from a 2 to b 2. This is our this one. So, this is a case a cell in R 2 space. in the R2 space, this is in R2 space like this. Now, what he says is, if in general if I take a K cell, then I be suppose K cell, in that case it is of the it will contain all the points of the type x 1, x 2, x k, where the each x j will lie between this. X 1 will lie between a 1 b 1, x 2 will lie between a 2 b 2, x k will lie between a k b k. So, this one. Okay. Now, let us suppose the distance between that is delta. Let delta be sigma b j minus a j whole square, j is 1 to k under root. This is our. So, if you look this one, this is the same as what? So, b 1 minus a 1 square plus b 2 minus a 2 whole square. Okay. So, this will be the same as if I picked up the 2 point x and y in this set, x and y. X is say x 1 x 2, y is say y 1 y 2. If we picked up 2 points, then the distance between x and y in this R 2 space topology will remain less than this number. So, obviously, then distance between x y in R k space, that is we are denoting by same x mod of x minus y, will be less than equal to delta, when if x belongs to I, y belongs to I. So, x is x 1 x 2 x n, y is y 1 y 2 y n. Okay. We wanted to show this I is compact. So, assume that, let us suppose I is not compact. Suppose that I, the K cell I is not compact. It means that out of open cover of this, any open cover if I choose, then it cannot have a finite subcover. So, that is there exists an open cover, say G alpha of open sets, open cover of I, which contains no finite subcover, that is the meaning of this if it is not compact. So, finite subcover. So, let us suppose this is our, say here is A I, this is B I, and here is somewhere X I. This is our say another point. So, when you choose let us take cover, let us pick up C j as a point, C j which is A j plus B j by 2. Okay. It means C 1 I am taking as A 1 plus B 1 by 2, C 2 I am taking as A 2 plus B 2. So, if suppose this is in R 2 space, here this is A 1, this is B 1, here is A 2, this is B 2, and this basically we have this this is our rect I interval. So, what we are doing, we are taking a point here which is the point C 1 C 2, C 1 comma C 2. C 1 is the middle point of this C 2. So, once you take the point, it will divide this whole I in R 2 in 4 parts. This will be a one cell, the another cell like this. Okay. So, by choosing this way, by choosing C j, we can get then the intervals A j C j and then the interval S is C j and the interval C j comma B j. These intervals will determine the cell, will determine 2 k cells. Suppose Q1, k cells Q1 whose union is I. This is what okay. Just like in case of R2 I have picked up that if you take this interval C1 C2. So, A1 C1, then C1 B1, similarly here we get C1 B2, C2 B2 and like this. So, we get the whole interval 2 to the power 2, that is 4 k cells we get it here. Now, if I is not compact, then at least one of the cell will not be covered by a finite, will not be compact, that is open cover of one of the cell will not have a finite cover, there will exist an open cover of one of the cells. Okay. So, at least one of them union. So, what is, since I is not compact, since I is not compact, so at least one of these sets Q1, say call it I1, cannot be covered by any finite subcollection of the open cover G alpha. Otherwise, if it is so, then I1 will be compact and contradicts to I. Okay. So, that will be next step. Now, picked up now I1. Now, pick up I1 now and again divide, again subdivide this I1 in a similar way as defined earlier and continue this process. So, when you divide again, you are getting I1 say, or I2 is one of the cell which is not covered by any finite subcollection. So, again I2 you again subdivide it and like this. So, continue this process. So, when you continue this process, then we obtain in this process we obtain a sequence say I n with the following property, The first is these i's which you are getting cell will be satisfy this inequality. I is covers I1, covers I2 and so on, they are of decreasing nature. Then second is that In is not covered, by any finite subcollection of the cover G alpha. And third is that if x is a point in I n and y is also in I n, then the distance of this x y in R k, that is mod of x minus by over I n. This is over I n, of course, in I n, which is in R k. This distance will be less than or equal to 2 to the power n minus n into delta, because here if this length is divided, then what you are getting? This is the 1/4 basically. When n is 2, you are getting the half 1 by delta by 2, delta by 2 and so on, n is 3 and like this. So, this will be divided by this I 1, I 2 and so on. Okay. Now, what is 1? 1 says, so obviously 1 will here, now 1 will imply, because they are of decreasing nature, and any finite subcollection of this will be non-empty. So, the intersection of this will be non-empty. So, by thus there is a point x star which lies in every I n, This follows from the results which we have already proved, that if I 1 covers I 2 covers I n, and if any finite collection of this, that is intersection of this, will be non-empty. Just now we have seen that I n's. Okay. Second one is, so if I x star belongs to some I n. So, I n is a in K cell, is part of the K cell. So, we can find some alpha. So, for some alpha x star, this will belongs to the one of the element, for some element of the open cover, say G alpha, because we have taken G alpha as a open cover of the I. So, this x star will belongs to some of the G alpha for some alpha. Okay, alpha. But G alpha is open. So, this star will behave as an integer point. So, we can find out a neighborhood around the point which is totally contained in this. So, there exists an R greater than 0 such that the distance y minus x star is less than R, will imply R is in G alpha, that is an integer point, that is nothing. Now, R is our own choice. So, let us pick up n, let n is so large such that this 2 to the power minus n delta is less than R. That is possible, because R is one C fixed. You can take n such a large, so that this entire thing remains less than alpha. So, if it is so, then what happen? This implies that by which you are choosing, they basically is in our I n also, because I n is satisfy this condition, that if x belongs to y n, then this is 2 and this is less than R. So, any element of I n will be the element of R. So, this implies that the distance y minus x star is less than or equal to 2 to the power minus delta, which implies that the element y which is in G alpha belongs to I n, which is subset of G alpha. So, every element of y n, I n will be in G alpha for some large n, for some, which therefore, for large n or so for particular n, I n is contained in the set G alpha. So, once it contained in G alpha, then I n is covered by G alpha, that is I n is covered by G alpha, which contradicts the second part of it. What is the second part? Says I n is not covered by any finite subcollection, but it is covered by the G alpha, that is a finite subcollection G alpha. So, contradiction, and this contradiction is because of a wrong assumption that I is not compact. So, therefore, I is compact. So, this proves the result, means every K cell is a compact. So, in particular every closed interval is a in that is a compact set, because that is also. Now, this gives a very interesting result, which we call it as a Heine Borel theorem. Heine Borel theorem. Okay. But basically this theorem says that the statement of the theorem, let it be, the theorem is Heine Borel theorem is, if we a subset K, a subset K of R, subset K of R is compact if and only if and only if it is closed and bounded, is closed and bounded. So, this is a particular when you are choosing R space. So, in general R K space we will prove some results. So, in a particular case we can say derive the Heine Borel result. So, the result is first that is important. The proof of this, the proof follows from the theorem, from the next theorem. What is this theorem is? The theorem says that if a set E in R K, if a set E in R K has one of the following three properties, has one of the following three properties, then it has the other two. That is, all three are equivalent, that is, the following three conditions are equivalent in the space R K. So, in particular when K is 1, it is also true in case of over the real line. What is the condition is? The condition says E is closed and bounded. Second condition shows that E is compact. Third condition tells every infinite subset of E has a limit point, in E. So, this thing, the proof of this. So, obviously, if it is true, then in case of R1, if E is compact, then it is closed and bounded, and vice versa. So, the result follows immediately. Heine Borel theorem follows immediately. So, let us see the proof. Suppose A holds, it means given E is closed and bounded, but we want to say E is compact. Okay? That is, E is closed and bounded. So, once it is bounded, it means it will be enclosed by some cell. So, so E is contained in I for some K cell I. Okay. But what is E? E is closed, but E is closed and I is compact, that we already shown. So, every closed subset of a compact set is compact. So, and we know that every closed this result we have every k is compact and every closed and compact sets are compacts. So, this is what we have proved earlier, closed subset of a compact sets are compacts. We know that every closed subset of a compact set is compact. This we have already proved. So, here E is closed, I is compact. So, E is subset of a compact set, therefore, this implies E is compact. So, once it implies means therefore, A implies B holds. Okay. Now, suppose B is true. Suppose B is true, then given suppose B holds, then automatically C implies. Why? Because V is means E is compact, that is E is compact. So, take a sequence, any sequence of the subsets of E. This we result already proved that if E is an infinite subset of a compact set, then he has a limit point, and we have shown earlier that if E is an infinite subset of a non-empty compact sets K, then E has a limit point in K, limit point in K. This we have shown. So, here E is compact already given. We wanted that every infinite subset of E has a limit point in E. So, what it shows is if this infinite subset of E, if I choose, and infinite subset of E means we can have it infinite subset non-empty compact subsets of K, then this will have a limit point in E. So, obviously, B implies C. So, that is nothing to prove is this. Now, to show C implies A, this we prove by contradiction. So, given that every infinite subset of E has a limit point in E. Okay. So, C is given, that is every infinite subset of E has a limit point in E. This is given. Okay. So, we wanted to prove A is closed, E is closed and bounded, but suppose E is not closed, not bounded, let it see first, not bounded. It means, if it is not bounded, it means there will be a sequence of the points in E whose bound will go to infinity, means each x 1, x 2, x n will be there, such that mod of x n will be greater than any arbitrary number n. So, we get then E contains the points x n with the property that mod of x n is greater than n when n is 1, 2, 3 and so on. X 1 will go greater than 1, x 2 so the limit of this x n will not exist. So, let S be the set of all such x n such that x n is greater, the mod of x n is greater than n. Then obviously, this is an infinite set, because if it is finite, then we can get the bound for x n. So, it is an infinite set, and clearly it has no limit point and has no limit point limit point in R k. This is the set we are choosing in R S concept. So, once it is, so it has no, hence has none in E, and hence not in none in E. Mean this sequence will not have any limit point in E also. Okay? That is one thing. Okay. Thus is bound. So, but what is this? This contradicts C, which contradicts C, because C says that if you take any infinite subset of E, it must have a limit point in S is an infinite subset of E, but it does not have a limit point in C. So, this implies that E is closed. Again, to show E is bounded, so suppose further assume C holds, but E is not closed. It means the limit point of the E, all the limit points is not in E. So, thus we can get the limit point, then there is a point, then there is a point, say there is a point, suppose x naught belongs to R k, which is a limit point of E, which is a limit point of E, but which is limit, but not a point of, but does not belong to E, because all the limits point does not belongs to E, because E is not closed. So, if it is not, then we can get this sequence of the points in E, that is, so the set x n belongs to E such that mod x n minus x naught can be made less than say 1 by n. This collection will be there, is it not? So, set of all points E which satisfy this a sequence will be obtained via this. Now, let us find S be the set of those points. Let S be the set of those points of each which satisfy this condition. Okay. We claim that S cannot has x naught as a limit, S has no other limit point, S has no other limit points, S with no other limit point except x naught, because if suppose y is another point of this, suppose if y belongs to R k and y is different from x naught, is a limit point, suppose, then we get, then the distance between x n minus y, because if y is a, then the limit point we will just go, because suppose y is another point which is different from x, then we can say x n by n is greater than equal to x naught minus y minus x n minus x naught. Thus, by but x naught minus y, because x naught and y naught is different. So, we can just put it as it is, x naught minus y. Now, x n minus x naught is less than, so minus of this is greater than minus. Now, n we can choose in such a way, so that the whole thing this is greater or equal to, the whole thing is greater than or equal to half of this. Now, y and x are different. So, this is fixed point. It means that this as n tends to infinity, x n does not go to y. So, this implies the limit of x n is not y. So, it cannot have a point other than x naught as a limit point, but x naught is a point which does not belongs to our set E. So, this sort y is not a limit point of any, thus has a no limit point in E. Thus, S has no limit, because x naught is not in E. So, S has no limit point, in E, hence contradicts our assumption 3, which contradicts C. Therefore, our E is closed. So, equivalence of 1 and 2 will implies the Heine Borel theorem. B will imply Heine Borel theorem. That is the proof for the Heine Borel theorem can be. Okay. Now, here we put some remark. The remarks say that in an arbitrary metric space, X D, the conditions B and C are equivalent. B and C, but A does not. It means in general B and C, A does not imply, but A does not imply B and C in general. It means for arbitrary metric space, the compact set and the infinite subset of E has a limit point are equivalent, but if a set E is bounded and closed, then you cannot say whether it remains compact or it will have a infinite subset of E will have a limit point in E. It is not, may not be true. For example, if suppose I take X as a Hilbert L2 space, L2 space means set of those sequences A n such that sigma mod A n square 1 to infinity is finite in L2 space. And if I take the sequence E n as 0, 0, 0, 1, 0, 0, this is the points belonging to L2 space. Now, if we take the norm of E n, now here norm of this, if suppose this I denote by A, then norm of A, of course, this is a case of function analysis, but I will, so we are not much going in detail, but this is the norm. So, norm of E n is 1 for each n. Therefore, E 1, E 2, E n, this set is there, E 1, E 2, E n and so on. Then each point having norm 1, is it not? So, it is bounded. So, S is bounded and none of the point is a limit point. No point is a limit point, because it is a point set only, limit point of S. Therefore, we can say all the limit points of S belongs to S. So, this shows H is closed also. So, it is a closed angle, but it is an infinite set. So, we cannot cover it by means of a finite subcover, but S cannot be covered by finite open sets, say G alpha out of open cover G alpha. Means any open cover here, we cannot choose the finite cover which comes, because it is infinite. So, it is not compact. It is not compact. So, this contradicts our. Okay. So, that is what we are not going detail for this, because it is a part of the functional analysis. The next result which we say is the Weierstrass theorem. The theorem says every bounded infinite subset of R k, every bounded infinite subset of R k has a limit point in R k. In R k. The proof is very easy. Since E, every bounded infinite subset, say E of R k has a, since E is bounded, which is infinite also, set is a subset. So, E is a subset of a k cell I, which is contained in R k, because it bounded means it will covered by some k cell. Okay. But what is the earlier theorem says that every k cell is compact, but every k cell is compact. Therefore, I is compact. So, E, which is contained in I, which is a compact set. Okay. And what this result says, the one result which we have already shown, that every, if you choose a infinite subset of a compact set, then E has a limit point in k. So, every infinite subset of compact set. So, if E is an infinite set of a compact set, infinite set of a compact set k, then E has a limit point in k. This we know, but we know this result. So, using this implies that our Weierstrass theorem, the proof of the Weierstrass theorem. Because Weierstrass theorem, we wanted to prove a bounded infinite subset of A has a limit point on R k. So, this completes the proof of this. Okay. Now, we have one more concept of set which comes in that is the connected set. Okay. So, let us define connected set. So, first we have a separated set, separated sets. Okay. Two subsets A and B of a metric space capital X are said to be separated if both A intersection B closure and A closure intersection B are empty set. Are empty sets. It means that is if no point of A, lies in the closure of B, and no point of B lies in the closure of A. Okay. Then we say these two sets are separate. It means this is the one set A and here is another set B. Okay, B, not this one. Now, if I take the limits points of A, all the point of A, then it should not belongs to the closure of B. And if we take any point of B, all its limit point, if it does not belongs to A, then we say A and B are separated. For example, if I take this set, say 0 1 and 0 1, suppose I take the set 0 1, B is the set say 1 2. If I look this, so this is the 0 1 and here it is 1 2, this is 1 2, this is. Now, if we look what is the closure of B, the closure of B is this. So, this is our 0 1 is the set A, and when you take this, then it becomes B 2, that is the closure of B bar, which includes 1 and open at 2. But 1 is a point which belongs to only B bar, does not belongs to A. So, neither the point of B nor its limit point belongs to A. Similarly, if we take the others, say this is 0 and 1, this is the closure of this, and the open sets, this one is 0 2 1 2 1 2 is our B. So, A bar intersection B is empty and A bar intersection B is empty. Then here A intersection B bar is also empty. So, A and B are separated set. Okay. There is a difference between the disjoint set and separate. Separated set of course are disjoint, but the disjoint set may not be separated. Separated sets are of disjoint, are of course disjoint set, are of course disjoint, but disjoint sets need not be separated. For example, if we look that interval 1 2, A is the set, suppose I take the interval close interval 0 1, and B is a set which is an open interval 1 2. Now, A and B are disjoint, A intersection B is empty. So, this implies A and B are disjoint, but A bar intersection B is not empty, A bar intersection B, because no, A bar A intersection B bar, sorry, A bar B, A intersection B bar is not empty, because when you take the closure of this, 1 is the limit point, 2 is also limit point. So, intersection will include 1. While the separate set said if both these are empty set. So, here at least this is not empty. So, this shows A and B are not separated. Okay. Now, we define the connected set now. A set E which is subset of X is said to be connected, if E is not a union of two non-empty union of the two, not a union of two non-empty separated set, separated sets. Okay. So, this is now one result we have in this connectedness over real line. What he says is a subset E, a subset E of the real line, R1 is connected if and only if it has the following property. The property says if x belongs to E, y belongs to E, and x is less than z less than y, then z is also in E. The proof is very simple. So, I will just give the outlines. If there exists, suppose if there exists a point z, if there exists x belongs to E, y belongs to E, and some z belonging to the interval x y such that z is not in E, then we will reach a contradiction. Then E can be expressed as the union of this set where A z is the set of E intersection minus infinity z, B z is the E intersection z infinity. Okay. So, since x and y are in ways, since x belongs to A because it is in E, and y belongs to B, and A and B are non-empty, and A and B are non-empty, since this is an all non-empty, then since A is the A z which is subset of minus infinity z, and B z which is subset of z infinity. Therefore, these are two separated set. Then obviously, A z and B z are separated. So, once they are separated, then E cannot be connected, set, because E is the union of these two sets. So, it is not so contradiction. Therefore, this result may not be true. This however, conversely, if suppose E is not connected, then there are non-empty separated set. Separated sets A and B such that their union A and union B is E. Now, pick up x and y. Now, pick up x belongs to A, y belongs to B, and let z is the supremum value of A intersection this closed set x y. Now, obviously, this set A clearly x belongs to the A closure, x closure, and hence this z belongs to A closure, and this z cannot belongs to B. Okay. So, what we get in fact, so therefore, x may be less than equal to z and strictly less than y. Now, if z does not belongs to A, then in case then we have x less than z less than y and z is not in E. If z belongs to A, then we have Z is not in B. So, we get there exists a Z 1 belongs to does not belongs to E, but such that Z 1 there exists a Z 1 such that Z x less than Z 1 less than by and Z 1 is not in B. Therefore, x less than Z 1 less than by, and this implies that Z 1 is not in by and Z 1 is not in by. So, this completes the proof. Okay. I think thank you very much.